very to another present here. It gives me immense pleasure to welcome you all to this special occasion where innovation, collaboration, and knowledge comes together under one roof. Today marks a proud moment as we host the Faculty Development Program on Quantum Computing. It is about celebrating the spirit of creativity and the pursuit of cutting its technologies. This FDP on quantum computing opens new doors for faculty and researchers to engage with the future of computation and technology. We aim to create a vibrant platform that reaches students, faculties, and industry experts, fostering both academic excellence and practical innovation. Once again, I welcome you. I now request our Honorable Dean Academics, Dr. S. Radharajan Sir, to address the dignitaries.
Hello, ma'am, am I audible? Ma'am, the voice on the other side is little low for me. Is it okay? Am I audible? Parvadam, ma'am?
Yes, madam, you are audible, but
Yes.
You are audible, ma'am. Yes.
So, am I to start or I heard something? Should I start?
yes, please, ma'am.
Just 2 minutes, we'll rectify this.
Procedure. It gives me to one and all procedure. It gives me immense pleasure to welcome to this week faculty development on quantum computing and its applications, organized by the Board of ECE of Sri Sairam Institute of Technology in association with IEEE. At the outset, I would like to warmly welcome our distinguished resource persons from industry and eminent institutes and researchers who have kindly accepted our invitation to share their knowledge and expertise in the field of quantum computing and its applications. I also extend my heartfelt welcome to the faculty members from various engineering institutions as participants and research scholars to join with us participate deeply. This program is specially designed to provide fundamentals of quantum mechanics for computation and hands-on exposure to IBM and insights into advanced applications like cryptography and quantum machine learning. Sri Sairam Technology has always strived to be a center of excellence in the education and research, and this FDP is yet another feather in the cap of Sri Sairam Institute of Technology. I am confident that this program will enrich our understanding. It will spark innovative research ideas and foster collaboration across institutions. Once again, I extend a warm welcome to all the dignitaries, resource persons, participants, and organizing members. Let us together make FDP a fruitful and memorable learning experience. Thank you.
Today, I have one of the first minds in the quantum computing industry, Dr. Manjula Gandhi. She is working as an associate professor at Coimbatore Institute of Technology for last 4 years and an IBM skipped advocate from September 2020. IBM Quantum Educator, IBM Certified Associate Developer Quantum Computation Qiskit, Mentor at Qiskit Advocate Mentor Program, translate lead or translate Qiskit textbook into Tamil. She's worked in the area of quantum computing from 2000
as part of MS and PhD. Her research interests include building reversible circuits, quantum complex graph algorithms, quantum learning, and quantum image processing. She was one of the guest invitees for the event. Kiskit India Week Quantum celebrate women in quantum. She has expertise in various quantum tools such as IBM Qiskit Classic, Microsoft QSharp, Xanadu Milane, and QSIM. She teaches quantum computing at CIT for last 2 years and has delivered quantum computing sessions in various institutions across India. We now welcome Dr. Manjula Gandhi to share her insights with all guests. Thank you, ma'am.
Yeah, good morning, everyone. I hope my voice is audible. Ma'am, am I clear?
Yes, ma'am, you're clear.
So let me share my screen. So, warm good morning to one and all present here, and my heartfelt thanks for the organizers for inviting me for this particular workshop. So, let me start. My today's talk will be on implementation of reversible logic circuits using quantum gates. And I'm actually working in quantum computing from 2003. As part of my MS by research and PhD. During my MS by research, I was working on graph theory based algorithms. And basically, this research was actually, initially when I started, we were working only on theoretical research. So later on, I started working on with simulators, which were existing in the period of 2009-10 and those days. So I did my PhD on reversible circuits, so designing quantum circuits, and where I was using simulators, quantum simulators actually. And 2015, I completed my PhD. And I would say 2017 onwards, now there are real quantum devices which are available. So I've seen this field as starting from theoretical research, moving on to working on with simulators. Now I'm really working on real quantum devices. So the transition from theoretical to hardware devices, quantum devices, has made me learn a lot more in I'll say invest more amount of my time into this particular field. So my today's talk will be a small sort of introduction, why quantum computing, transition from bits to qubits, some of the important concepts of quantum site, frameworks and applications of quantum computing, how to work using, I'll be using a demo on IBM's Qiskit. So I'll show you how to work on IBM Qiskit, which is free actually. You can use it, and it is an open source tool and it can be used. I'll tell you how to work on it. We'll be discussing single qubit quantum gates, multi-qubit quantum gates, and some of reversible circuits. So one circuit, how to build quantum entanglement. I'll also tell you what is GAZ circuit. If I have time, I'll be moving on with implementing classical logic gates using quantum gates. And the last part of my talk will be, I'm actually an IBM Qiskit advocate from 2020 onwards. So I'll tell you how to become an IBM Qiskit advocate, how you can spend your time in investing and become an Qiskit advocate, and what are the benefits of becoming an IBM Qiskit advocate. Assuming my voice is clear, my screen is visible to all of you. Is everything fine? I'm moving on to my, ma'am, I just want to know whether my voice is clear and my screen is also visible.
Yes, ma'am. Yes, ma'am.
Okay, ma'am. Thank you. So, yeah, the main thing why we are moving on to quantum technologies or quantum computing, right? Because our classical machines which we are having right now, they use a concept of irreversible circuits. The circuits which our current day computers use inside them they are irreversible. That is, we can only walk from input to output, and there is no vice versa. That is, we can't walk from output to input. So that is one of the major drawbacks. And what Landrer and Feynman they was, if at all, if our devices do generate heat, the loss of data which we are not able to take. So we are working from input to output, and after getting our output, we lose some of our inputs. That loss of data is actually generated as heat. And if at all, if this heat dissipation has to be reduced, what people like Landrer and Feynman, what they suggested was, instead of irreversible circuits, the circuits behind our system should be reversible in nature. Reversible in the sense, I should be able to walk both the ways, from input to output and from output to input. So only if that is possible, our power dissipation can be reduced. This is one. Second is miniaturization of our integrated circuits. Sizes that is getting decreased. That is, we are at the end of Moore's law. So what next is what? Quantum computing comes into the reality nowadays. And why we are talking about reversible operations in quantum? Because all circuits behind quantum machines are reversible in nature. This is from an IBM quantum system. So quantum machines use the concept of quantum mechanics. A classical machine uses the concept of classical mechanics. In normal computers, we use bits, that is 0 or 1. Whereas in quantum computers, we use something called as qubits. We also call them as quantum bits, where I can not only be in state 0 or 1 at a particular time, I can be in 0 or 1 or on both the states at one particular time. I'll show you how I can be in both 0 and 1 at one particular time. And that made me, this concept made me not to leave quantum computing during my early days of my research, because we can compute on 0 and 1 at one particular time. So that is the advantage of working on quantum systems. So how does the use of qubits affect computation? We are in classical machines. The data unit which we use is bits, which can either be 0 or 1. So at a particular time, we can be in state 0 or it can be in state 1. Whereas when I'm talking about a quantum computation, our data units is qubits, that is quantum bits. And we use quantum mechanics bracket notation. This is ket notation. We read it as ket 0, ket, K-E-T, ket 0. An upward arrow indicates this is state 0 and a bottom arrow indicates I'm in state 1, that is state 1. So a state xi, an arbitrary state xi, whereas when we are looking into a classical machine, we can be in state 0 or 1 here. But when I'm talking about a quantum machine, I'm in ket 0 and this is ket 1, and this is a state where I'm in both my states, 0 and 1, 50% of zeros and 50% of 1. We call this as a state where I'm able to exist in both the quantum states. And in general, an arbitrary state, ket xi, this one, we read it as ket xi, is represented using C1, ket 0, plus C2, ket 1. And what we have an additional condition here is, the sum of my squares of my amplitudes should sum up to 1. Say, mod of C1 square plus mod C2 square should sum up to 1. That is the constraint here. So if I'm saying, if this is our state, the probability of measuring 0 will be norm C1 square. The probability of measuring 1 will be norm of square norm of C2. That is what we say. Say for example, if I have 1 by root 2 ket 0, 1 by root 2 ket 1, in that case I could say I'm in 50% of measuring 0 or 50% of measuring 1 at a particular point of time. So we are actually moving from bits to qubits, from classical computations to quantum computations. So ket 0, ket 1, and we can be in both the states 0 and 1, and we can make computations on 0 and 1 at a particular time. Let us consider a small scenario here, assuming we are running a travel agency where he's owning 2 taxis and there are 3 people. A tick indicates that A and B are friends. A cross indicates that A and C are enemies and B and C are enemy pairs. And the scenario here is, there are 2 taxis, taxi 0 and taxi 1. 0 indicates we are in, that is A, B and C are traveling in taxi 0. When I'm considering this particular case, A and B are traveling in taxi 0 and C is traveling in taxi 1. Similarly, if I consider this, A is traveling in taxi 0, B and C are traveling in taxi 1. So here we have, there are 2 taxis and there are 3 people. So the total number of configurations which we have is 8 different configurations. So the configurations are all 3 are in taxi 0, or A, B in taxi 0, C in taxi 1. Like this, you can read out all your 8 configurations, and we actually calculate this configuration score. How do we calculate the configuration score? Is by using this particular formula. The score for the given config for a given configuration is given by number of friends sharing the same car minus number of enemy pairs sharing the same car. Our thing is, if we are traveling along with my friend, my journey will be peaceful, right? So that what we do is, so friend pairs sharing the same car minus enemy pairs sharing the same car. So here the friend pairs are, we have A, say for example, if I consider A, B and C, A and B are friends and C is enemy. So here A and B, the number of friend pairs is 1 and there are no enemy pairs because C is not joined with anyone. So we have the configuration score for 001 as 1, and similarly the configuration score for 110, that is when A and B are traveling in taxi 1 and C in taxi 0, this particular last second one will have a configuration score of 1. And for all others, my configuration score is -1, saying that the value, the one which has the highest configurations are the results for this particular scenario. So this A and B can travel in taxi 0, C in taxi 1, or A and B in taxi 1 and C in taxi 0. So these are 2 solutions which we get for this particular scenario. Now let us increase the number of friends and enemy pairs. So instead of 3 people, I've taken it for 4. So 2 to the power 4, which we have, where we have 16 different configurations here. So here again, additional friends and enemy pairs are being introduced, and we have 16 configurations here. So we can calculate the configuration score again by applying the same formula: number of friend pairs sharing the same car minus number of enemy pairs sharing the same car. I can write a small C or a Python program to calculate the configuration score when I'm having 4 people to travel in 2 taxis, and additional friends and enemy pairs constraints are added to it. Now what will happen, instead of 4 people, I'm incrementing the number of people as 100 people, and instead of taking cars, let us take it as bus. So we have 2 per 100 configurations, which is actually 10 to the power 30, which is 1 million configurations, which is actually impossible for us to solve using our classical computers. So this is where we are in need of quantum machines to compute our operations with. So solving the same problem, the travel agency problem, using a quantum machine, if I'm using a single qubit machine, I can use 0 and 1. That is, I can compute on both 0 and 1 pairs and work. If it is a 2 qubit machine, I'll have all my configuration scores as 00, 01, 10, and 11. So 2 qubit machine computes on all of these 4 pairs at one point of my time. It will take only one operation of my time for computing on all of these 4 values. This is our example for two taxis and 3 people. So ABC are people, and taxi 0 and taxi 1, all your configurations 000, 001, etc. up to 111. So it will only take us one operation of time for computing the configuration score for all of these 2 to the power 3, that is 8 different ways, in one operation of my quantum program. If I increase the number of qubits, if I go for a 4 qubit machine, I'll have 2 to the power 4. That is all 16 configurations which we have. We can compute the configuration score for all 16 ways in one operation of your quantum program. Similarly, increase the number of qubits. So 2 to the power 5, 32 different values, 2 to the power 6, 64. Like that you can go on. And 2 to the power 127. So earlier we used to have very less qubits with us, but now there are devices which supports more than 127 qubits to solve a particular quantum program, write the program, execute it on the device and get your solution. So that is the advantage of quantum machines. So they work on a concept of parallel universes. So I can compute on 0 and 1 at one particular time. Parallelly, I can work on both 0 and 1 at the same time. So our operations taken, if at all, if I'm talking about a classical machine, we need 10 to that is when we had 2 bus and 100 people configuration. So we need 10 to 30 operations in a classical machine. But whereas when I'm talking about a quantum machine, it is enough in one single operation of my time. I can compute for all of my values. The drawback of quantum machines, the drawback here is what happens is quantum systems are prone to errors. So errors in the sense, when I'm running my program for the first time, I might not get my first best solution. What it will do, it might give me the second best solution or my third best solution. So what we do, we run the same program for multiple number of shots. I'll devise a code, I write a code and I run it for more number of shots. Say for example, if I'm running it for 1024 shots, I could say for 1000 shots, if I've got my answer correctly, I would take the one which gives me the answer for majority of my times is going to be a solution. So it is which is much far better than going for these many operations, 10 to 30 operations on a classical machine. Another example for why quantum computing. Assume we have an equation here, y is equivalent to 2x square plus 4z plus 2. So I'm having a quadratic equation here and I'm assuming that all my x and z are quantum numbers and they are represented using 3 qubits. So 3 qubits in the sense 0 to 7. So z can take values from 0 to 7, x can take values from 0 to 7. So what we are actually doing is in one single operation, I can compute y for all values of x and all values of z. That is the advantage of quantum machine. So that is when x is equivalent to 0, when z is equivalent to 0, what is y? When x is 0, z is 1, what is y? When x is 0, z is 2, what is your y? Similarly, x is 0, z is 7, x is 1, z varies from 1 to 7, x is 7, z varies from 1 to 7. So if I'm talking about a 3-qubit machine, if my x and z are 3 qubits, so for all values of 0 to 7 of x and all values of 0 to 7 of z, I can compute y in one operation of your quantum program. Suppose if I'm incrementing my number of qubits here, if x takes 4 qubits. So for all 0 to 15 values of x and 0 to 15 values of z, we can compute y in one operation of your quantum program. So these are a small glimpse of why people are talking about quantum computing and how we can use them in our programs. So the next part of my talk is I'll be talking about some of the important concepts of quantum world. The first one is superposition. The one which I was right now talking, I can be on both states at one particular point of time. I can be in state 0 and state 1 is called as superposition state. We had a fight. I had a fight with my supervisor when he was saying, how can you be in both 0 and 1? Show me how can you be in 0 and 1 at one particular point of time. Those days I was not having devices, or I was not having, I would say IBM Qiskit I didn't have, so I was not able to show him that this is what a superposition state is. But now I can easily show you I'm in a superposition state and this is how I create a superposition state. I'll show you in 1 or 2 minutes after, in the next part of my talk, what superposition is. So superposition is a state where I can exist in multiple states at once. That is at a single particular point of my time. I can exist in both the states. So that is superposition. Next one is interference. There are 2 types. One is constructive interference, another one is destructive interference. That is when waves overlap, we'll have constructive interference. When they depart, we have destructive interference. And the next part is we have measurement, how to measure qubits. So qubits, they be in their own state, zeros, ones, zeros, and ones at a particular point of time. But once when you go for measurement, they get destroyed and they land up in one particular state. So that is one thing which we have to look into. So measurement plays a vital role in quantum world. You measure qubits and store it in classical bits. I'll show you how to make a measurement on a qubit and how to store them. And the next concept is entanglement. So I also have entanglement slides. I'll be discussing with it. And there were two algorithms. One was Peter Shaw's factoring algorithm, which he devised in the year 1992, and Grover search algorithm in the year 1994. What did Shaw say was, he said, you can break up a very big number. That is, factoring a number is very easy if at all if quantum devices comes into existence. Our current day our current day passwords, all your Gmails, your bank accounts passwords are working just because of we cannot factor a very big number. So RSA cryptography technique. So what the thing is, if quantum systems comes into existence, you can easily factor a number by using Shah's algorithm. There is a very good video on Peter Shah's factoring algorithm, how he devised and how it works and those things. Or maybe later part, Ashwat probably he might touch quantum algorithms. And global search algorithm is you can search a very big database in the order of square root of n times. So that is normally a classical algorithm. We go for order of n. But here, using a Grover search technique, you can find your solution in order of square root of n times, which is very, very huge. So after these two algorithms came into existence, people started working on to quantum computing, and that is where we are here today, organizing FTPs on quantum computing. So the next part, there are various quantum computing frameworks which are available. I initially started with Microsoft Fuchsia, and one small note, all these are open source tools for you can use them for your research, for education purposes. And then later I started with IBM Qiskit. Classic again is a high level quantum programming platform, and IBM Qiskit is actually you go for designing low level circuit designs, whereas Classic you can write high level code. Circuits will be auto generated for us, and you can execute your code on various devices which are available. They are connected with many other platforms. Just log in, use your educational mail ID, and you can get access for accessing those platforms. If you people are interested in machine learning, I would suggest to use PennyLane of Xanadu, and Google's product Circ, again similar to Qiskit, TensorFlow Quantum, and QSIM is India's product, Quantum Simulator, and this is a link for qctoolkit.in. All these are open source; they are free for using, and various applications where you can find quantum computing into existence. I've worked on most of these things. I initially worked on, for my PhD, I've worked for designing reversible circuits, building up quantum software. I could say Qiskit is a software, IBM Qiskit, Circ, Classic. So people are investing more amount of their time in developing quantum softwares. If you are circuit branch students or researchers, I would suggest invest your time into quantum hardware. Quantum machines, like we are in a state where people are competing. IBM is there, NVIDIA is working on, Google is working. Many people are investing on quantum hardware sections. So if you're interested, you can move on to quantum hardware, machine learning, and anything which you have learned in your classical side. Say if you are good at machine learning, I could say look at the counterpart of quantum machine learning. If you are good in image processing, if you are at compilers, if you are building games, classical games, why not go for building up quantum games? There's a person called James. So imagine if it is 2 to the power 156, how many parallel computations I can make. So Flamingo in the year 2026, 10K, Flamingo 10K, which again 2027, 15K, Starling, 200 qubits it's going to support. So by end of 2033, they are planning for 2000 qubits. And This is the scenario which is currently happening. And the platform, you can note down this link. This is a link for creating user ID onto IBM Quantum platform. So I will be logging into my login ID and show you how it will work. So how you can run algorithms on quantum computers. We have 3 steps. First thing, I should decide the number of qubits that is the circuit, how many qubits I'm having, and what is my algorithm. So what my algorithm is made up of, combination of my quantum gates. So the next part of my talk will be what are the various gates which we have and how we can apply them. And then finally measure your qubits and store the results in classical bits. So classical bits, we are going to store them either as zeros or ones. So this is a sample quantum circuit here. Let me take the next slide. So here I have Q0, Q1, Q2, and Q3. They denote qubits. So Q0, Q1, Q2, Q3 are your qubits, and this double line indicates they are classical bits. And these gates are the gates. These are single qubit quantum gates because I've applied X on Q0. I've applied one gate here on Q0 and Q2. So these are multi-qubit gates, a 2-qubit quantum gate, and this is a 3-qubit quantum gate. Again, this is a multi-qubit quantum gate. So we have a quantum circuit here of 4 qubits and 2 classical bits. I hope you are able to follow me. There are 4 qubits. Each line is for 1 qubit, and there are 2 classical bits here. And what are these symbols denote? They are measurements. You measure Q2 and store it in classical bit 0. You measure Q3 and store it in classical bit 1. It does not mean the value 0 and 1 for Q2 and Q3. And this 0 indicates C0 and this 1 indicates C1, where it goes for classical bit 0 and classical bit 1. So reversible circuits are those circuits that do not lose information. Reversible circuits can generate a unique output vector from each input vector and vice versa. In reversible circuits, there is a one-to-one mapping between input and output vectors. This is an example for irreversible AND gate. So here what happens? I've given A and B as our inputs, and we go for A and B is your output. If the value of A and B was 0, it is impossible for us to say the value of what my A was or my B was, right? Because we have lost the data. So since we are losing the values of our inputs, and that loss of data is what is generated as heat in our current day classical systems. Whereas when I'm talking about a reversible AND gate, here we have one-to-one mapping between our inputs and outputs. I can walk from input to output and walk from output to input. So there is no loss of data even after measuring my output. If after measuring my A and B, the value of A and B are retained. So this is what classical quantum circuits are built on. So quantum circuits are built on the concept of reversible logic. You have one-to-one mapping between your inputs and outputs, and we don't have any loss of data here. So before moving on with my the next part of my talk, let me show you how to log into IBM platform. So quantum.cloud.ibm.com. I'll just copy this in chat link. IBM Cloud Platform. This is a link for creating your for logging in. So it will take you to this particular screen. Here we have there is a sign-in option here. You can, for the first-time users also, you'll have a drop-down. You'll have, are you using for the first time or something? So let me show this particular screen. I'm logged in. I've already logged in actually. So what will happen is you will have a sign-in option here. You are supposed to do your, you want again log off. Just click on the sign-in. It will ask you whether you're first-time user. So you'll have a sign-up over there and you can proceed with that. So once if you log in, create an ID and log in, you will have, this is the home page. You have a menu here for instances, for workloads, your documentation, your learning. And learning is what will help you to quantum learning. So you have many courses available for free here. So basics of quantum information, fundamentals of quantum algorithms, general formulation of quantum information, quantum computing in practice, QML, VQE, variational quantum eigensolver, quantum chemistry people. All of these, whichever line you're interested. I would say the first course which you could do is Quantum Business Foundation. You will get a credit badge after completing this particular course. You can start with this and then move on with fundamentals of basics of quantum information, maybe your second one. And your third one can be fundamentals of quantum algorithms. And then you can proceed one by one, depending upon what is your area. If you are good at materials, you can go for that. If you are good at sensing or quantum communications, quantum cryptography, quantum machine learning, whatever you want, you can just look at. Today's talk, I'll be looking into, and there are resources like tutorials are available, YouTube videos are available for computer science people, and for quantum mechanics, if you want the basics of QM, you can also go here. And we have a portion called as Composer. So I'm just exploring Composer here. Let me open it in a new tab. So Quantum Composer will look like this. So from where did I come? From the learning of my IBM, I'm into my Quantum Composer. So this is a dashboard of, for I would say early or first time users or beginner stage quantum computing users can use Qiskit's Composer, which is just a drag and drop view where you have and you can visualize them. So here the dashboard contains, you can name your quantum circuit here, demo. And then these are various qubits which are, various quantum gates which we are having. So I'll be talking about these quantum gates and I'll show you the demo of working with these quantum gates in the next part. Next we have qubits. The circuit line which I showed you right now, Q0, Q1, Q2, and Q3. So this is a quantum circuit where we have 4 qubits and there are 4 classical bits. Say if I want to reduce my classical bits, yes, I can decrement them. I can reduce it by selecting minus sign, or if I want, I can also modify this. The right part of my screen is custom code, which is auto-generated here. So if I modify it here, you could see C2, it changes. If I want just one classical bit, either modify it here, or you can go and add or delete here. You have a plus and a delete button over there. So if you want, you can add. So they are dynamic. So C2 changes here also. And these are your quantum bits, Q0, Q1, Q2, and Q3. And these are your classical bits. And the bottom of my screen shows the visualization sections. So if I'm here talking about a 4-qubit machine, so we'll have all the values from 0, 0, 0 to 1, 1, 1, 1, 4 ones. Okay, so that is from 0 to 15. If I'm talking about a 5-qubit machine, 2 to the power 32. So Composer will only allow us to work with 4 qubits. If your quantum program consists of more number of qubits, you can go for installing Qiskit locally on Anaconda and pip install Qiskit. I'll show you that portion also. For working on with more number of qubits, you can go for local installation of Qiskit, or you can use QBraid. QBraid also has, you can just create a login ID over there and you can work on rather than local installations, or Collab will also help you in working. And this is my output visualizations. We have state vector visualization, we have Q-sphere visualization, and what are these that I'll be talking in the next part of my talk. So we have the gates which are available here. And this is your circuit design page. You can add qubits, you can add classical bits, remove qubits, remove classical bits. And these are your probabilities, and these are your output visualizations. And this is your custom code, which is auto-generated for us. You can save your file, you can do whatever you want. And the next, you can set up and run. After writing your code, you can execute your program. onto real quantum devices which are there. So, for example, I have access to Brisbane, which is right now online. The processor which it uses is Eagle R3. The number of qubits it supports is 127 qubits. And right now, the number of pending jobs on this system is 4,615 jobs which are pending. Similarly, for IBM Torino, Iran processor is used, which goes for 533 jobs are pending. So you can execute your code, you can implement your whatever code you're doing, you and come and execute it on real device if you have access to those devices. Earlier, these executions were free actually. But now we have pay and use for devices, the other devices which I have. Right now, I'm closing this. If you're having any doubts, I could take and then proceed with my talk. Any doubts, anybody? So the next part of my talk is representing qubit states.
Some questions are posted in the chat box, ma'am.
Yes, ma'am. Do we have quantum finance related courses? Can professionals start from the beginning? Can professionals register and use for free? Yes, sir. Yes, ma'am. You can register and use it for free. All the courses which are, all the platforms which I told are free. You can access them. No issues. And do we have quantum finance related courses? Finance related courses, I could say there are existing use cases available. Maybe you could find papers related to quantum finance, not specifically course from IBM related to quantum finance. There are journal papers available related to finance. Shall I move on now?
Yes, ma'am.
So representing qubit states. So how do we represent qubit states? We have three different bases when I'm talking about IBM's Qiskit. So one is Z basis, the other one is X basis, and the third one is Y basis. So in Z basis, there are two eigenvectors, state 0, ket 0 and ket 1. So a state in Z basis can either be state 0 or state 1. And when I'm talking about X basis, we'll be in state plus and minus. I'll tell you what is plus and minus in two more minutes. And in Y basis, we can be in states I and minus A. For the right moment, I'm not doing much of math here. So we use direct bracket notation from quantum mechanics. And we represent our quantum states using vectors. I want you people to note down, ket 0 is denoted with this one. So 1, 0, it indicates I'm in 100%, I'm in state 0. If I go for 0, 1, I'm in 100% in state 1. That is amplitudes here. We don't have 0 here, so we have 100%. So 100% of probability when I measure this particular state, I'll be in state 1. When I'm talking about this, when I measure this particular vector, 100% of my measurement, I'll be in state 0. So qubits are represented by 2D vectors. A general state Q is given by cos theta by 2, theta is over here, and cos theta by 2 ket 0 plus E I phi sin theta by 2 ket 1. This goes for your phase change values, and this is for your amplitudes. E I phi is for your amplitude phase change, and cos theta by 2 and sin theta by 2 go for amplitudes or measurements for 0 and 1 respectively, and theta and phi are real numbers in this particular diagram. So just note down what is ket 0. Ket 0 is denoted by 1, 0, And Qiskit is upon Python. So I'll show you how Ket0 is represented in state vector representation using Composer when I move on there. So Z basis, we have 0 and 1 as our orthonormal basis. So we have Ket0 and Ket1. For X, we have plus and minus. Your plus state is denoted using this. That is, I'm in 50% 0. I'm in 50% 0 and 50% 1. So when I talk about Ket plus, we have 1 upon root 2, Ket0 plus Ket1. So in your vector representation, this 1 by root 2, 1, 1. So I'm in 50%. That is, if I square 1 by root 2 square, how much I'll get? I'll get 50%. I'm in state 0 and 50% I'm in state 1. Similarly, for minus state, it is 1 by root 2, Ket0 minus Ket1. So 1 by root 2, 1 minus 1. This is your vector representation for minus state, which we also call it as 1 by root 2 Ket0 minus Ket1. And I'll be showing all of these states using Composer. Next is Y basis. In your Y basis, we have I and minus I. That is clockwise and anti-clockwise rotations. So the vector representation is 1 by root 2, I by root 2 for plus I, 1 by root 2 minus I by root 2 for minus I. So here, or if you want, you can write it like this. So 1 by root 2 Ket0 plus I by root 2 Ket1. For minus I, it is 1 by root 2 Ket0 minus I by root 2 Ket1. This is for, there are 3 different bases, and we'll be seeing these bases in our outputs. Superposition state. So how we can create a superposition state is my next part of my talk for a single qubit machine. So I'm in state 0 and I'm in state 1. So if this is the general representation of a qubit in a superposition state. Alpha Ket0 plus beta Ket1. Alpha and beta can be any arbitrary complex numbers whose squared moduli should sum up to 1. So alpha square plus beta square should sum up to 1. So if I say mod of alpha square is going to be the probability of measuring 0 in this particular state. You are given a state like this, take this alpha, square it, and that will give you the probability of measuring 0. Similarly, if I take beta square, that will give me the probability of measuring 1 in an arbitrary quantum state. Okay, this is for 1 qubit system. I can be in state 0 and state 1 at a point, both 0 and 1 at one point of my time. If I'm talking about a 2 qubit machine, so this is a 2 qubit system. I can be in all my 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. So all of your 4 states and your sum of your squares of your amplitudes should sum up to 1. Say if I'm asking you find the probability of being in state 0, 1, what will you do? You'll take square of alpha 2, and that will give you the probability of being in state 0, 1 in this particular arbitrary quantum state. Similarly, if I'm talking about 3 qubit machine, I'll be having 0, 0, 0, etc. up to 1, 1, 1, where I have alpha 0 to alpha 7. And sum of my squares of my amplitudes should sum up to 1 for the state to be a valid quantum state. Similarly, for 16 states, 16 bits, 16 qubits, etc. up to 2 to the power n states. So each time you add 1 qubit, the number of possible states doubles. So hence, quantum systems grow exponentially, and that is the advantage of working on with more number of qubits. So imagine if you are going to have 2,000 qubits, the amount of operations which you can perform on all of those qubits is huge and tremendous for us. So that is why if quantum devices comes into existence, you can parallelly work on your Shah's algorithm, your Deuces-Jones algorithm. All quantum algorithms are really very, very useful quantum algorithms where you can explore. And if you're having time, or maybe later my friends will be handling sessions on quantum algorithms of DG algorithm, Shah's algorithm, Grover's factoring algorithm. Many algorithms are quite useful for many use cases which are there. So before moving on to this, let me show you how to create a superposition state using Composer and then come back here. So let us go to our Composer. I'm deleting all of my qubits. I just want 1 qubit here. So let me take a single qubit machine. and it is enough. So you could see whatever I delete here, I'm modifying it. This is also auto modified. Your custom code is auto modified. Your bottom of your screen, your probabilities, your Q sphere, everything will change. Table view or graph view, all our things are getting changes over here. So now I'm going to create a superposition state. So the gate which is used for creating a superposition state is Hadamard gate. This gate was not there, or composer was not there for me on those days. I would have shown my supervisor that this is what my state 0 and state 1. I'm in both 0 and 1 at a particular point of time. So I have a qubit called as Q0. I have a classical bit called as C1. I'm applying a gate. I've just dragged and dropped my Hadamard gate here. So just drag it out, put your Hadamard here, and look at the values here. So what has actually happened? So we are in state both 0 and 1 at a particular point of time. I can download it in any format, whatever I want. This is my Q-sphere representation. I can also show you your state vector representation of this. So this is for a single qubit superposition state. 0.707 is actually 1 by root 2's value. So we had 1 by root 2 get 1, right? 1 by root 2 get 0 plus get 1 was my state vector representation for had a plus state. So what we actually have done here is I'll just put 1 0 here for you to show you what is actually happening. Initially, all qubits are in state 0. And let us inspect this particular quantum state. So I'm starting from 0. So you could see we are in state 0 here. So we are in state 0. I'm applying Hadamard gate. I'm in state both 0 and 1 with a probability of 50-50. And if you have noticed, look at the state vector representation here. For 0, I told you the vector representation for get 0 is 1, 0, right? And since Qiskit is on Python, complex number notations, and we use A plus B, J format here. So 1 for get 0, it is 1 plus 0J, comma 0 plus 0J in state vector representation. So state vector representation for each of your states. So this is for get 0, this is for 0 and this is for 1. So I'm having a probability of measuring and being in state 0, a probability of 100%. Now I'm applying Hadamard gate. So look at the probabilities. We are in state 0 with a probability of 50%. We are in state 1 with a probability of 50%. And look at the state vector representation here. This is 1 by root 2 get 0 plus 1 by root 2 get 1. So this is your state vector representation here. And I'm just inspecting my circuit here. Let me add a measurement. This is your measurement symbol here. If I measure it, what will happen is I'll be either in one of my states. So why? Because measuring and storing it on a classical bit will collapse. The qubit will collapse and it will land up in one of your states. So if one run I'm running this and be in state 1. Next again, if I'm running it, I might be in state 0. It depends upon whatever probabilities you have. So you're measuring. Look at the code which is auto-generated here. Reset is for, I've just inserted 0 to show you what get 0 will look like. So we have quantum registers. How many classical registers we have? We resetted our Q0, applying Hadamard gate onto Q0, and I'm measuring Q0 and storing it in classical bit 0. So this is read as measure Q0 and store it in classical bit 0. So I'm measuring Q0 and storing it in classical bit 1. So this is how creating a single qubit superposition state will look like. Let me add one more qubit here. So we have Q0 and Q1, and I'm adding another superposition state. Let us also add this one. Let us add one more qubit also. We'll again start from 0 and again apply a Hadamard gate. So if you could see this scenario here. So why it's not changed? Let us inspect this particular circuit. So we are starting from all your qubits. So all are in 0, 0, 0. So your computational basis states. So right now I'm in 0, 0, 0. So the amplitude for your kid 0, that is 0, 0, 0, 0, 0, 1, 0, 1, 0, etc. We are not in any of our states. So it is 1 plus 0 j for the state 0, 0, 0. Next is I'm applying Hadamard onto my qubits. So after applying Hadamard, so what is actually happening? So you are put in a superposition states of zeros and ones. And let me do one thing. Let me stop this, delete this measurement. Measurement collapses. I want all in states. So this is our initial, now let us inspect. So this is 0, 0, 0 initially. I'm moving to next applying Hadamard gate. So Hadamard on all of your qubits puts in a superposition state. And this is your state vector representation for 2 to the power 3 states. And we are in equal probability of 0.354 square will give me measurement of state 001. The probability of measuring the state 001 is actually equivalent to 0.354 square. That is what my value is for the probability of measuring 000 or 001 or 010 anything. Okay. So while stopping inspect, while in inspect, you can't modify this. So you should stop inspect here, and then you can drag and drop whatever qubits you want, whatever gates you want, add qubits, delete qubits, anything you can do. Okay. So this is our three people traveling in 2 taxis. So taxi 0 and taxi 1, your algorithm will write you're put into an equal superposition state of all 3 qubits, write your code for the configuration score what you want, and based on that, whichever is going to be your solution will have these amplitudes to be high. For all others will have a lower or 0 amplitudes for as your solution. Okay. So this is how you create superposition state. Do you want me to repeat, ma'am?
Madam, I have one question.
Yes, sir.
For qubit, one qubit, there are 2 positions, right? I mean, 0 and 1. And you have shown a matrix 1, 0, right? Where if it is in 100% probability, then 1, or otherwise 100% probability 0.
Yeah.
But I see in this on a screen when you selected a 3 qubits for 0, 1, 0, 0, 0, and 7 zeros I see. So on a probability basis, if it is a 1, I mean 100%, then 1, and whatever probability values for
the visibility was when I applied Hadamard this H gateway.
no, before that.
Before this, shall I delete this?
Yeah, or otherwise, is it possible to enact it?
Yeah, I'll explain. I'm just deleting all of these.
No, ma'am. You can just keep it. Now, if you see here, in this state vector diagram below, I can see the vector 1, 0, 0, 2. So how do I, interpret this one? On
this interpretation you are in need of, right?
Yes.
So this you read it as 0, 0, the first one. Next one is for 0, 1. Third one is for 1, 0, and fourth one is for 1, 1. This is how we read. And one thing which I have to talk here is, so let me take one NOT gate. This is your NOT gate here. I'm just doing one to show you what is actually happening. What NOT gate does is it just flips your qubits. Okay. So initially I'm starting here. I'm in state 0, 0. So we are in state 0, 0. And look at the state vector representation. These 4 values goes for 0, 0, 0, 1, 1, 0, and 1, 1. So there are 4 values here. And now what we are actually doing here is I'm applying NOT gate to Q0. Keep in mind, we are applying NOT gate to Q0, and Qiskit uses little NDN notation. I'll type in chat. It uses little endian notation. And what do I mean by little endian notation is, this is your Q0, your right end of your state vector. So this 1 is your Q0, this 0 is your Q1. If I'm increasing one more qubit, my Q0 will be to my right end, next comes my Q1, and next comes my Q2, Q3, and so on. So now what happens? I've applied NOT gate onto my Q0. So from 0, this changes to 1. And your state vector representation for 0, 1 is going to be the highest one. So it has a highest amplitude, and we read it as 1 plus 0G. Okay. And again, if I want 1, 0, what I can do is I can apply my NOT gate here. So this is, I'm applying NOT gate onto my qubit, second qubit, that is Q1. So your Q0 is 0 and your Q1 is 1. And look at now, we'll have 1 plus 0J over here. Similarly, if I'm adding another NOT gate to both of my qubits, right now we are in the state of 1, 1. So this is how this works. Did I answer your question? And all these are represented using complex number notation, sir. Or if this is getting confused, what you can do is you can better go for a single qubit notation, understand how a 0 state will look like. So now let us inspect this particular circuit. So I'm initially starting from gate 0. So your gate 0 is represented as 1, 0. This is how you represent gate 1, 0. 1 on top line, first row, 0 on bottom line. So that was my vector representation for gate 0. If I move on, I'm moving on to 1. So now for 1, it becomes 0, 1. Understood?
Got it, ma'am. Thank you.
So this is how you represent your state vector, your qubits in state vector representation. And since we started this, let me finish this using Q-sphere also. So we have state vector representation near your vector representation of for what? For 0, get 0. This is your, please note down this also. This is your state vector representation for get 0. I'll repeat. We saw vector representation for get 0. This one, right? Get 0, you write it as 1, 0. And using state vector representation, you write this as 1 plus 0J and comma 0, which is supported by Cricket. We also have another representation here. Let me stop inspect. Let me go and show you Q-sphere representation. And is this screen visible here? Can you see this diagram?
Yes, please.
So this is Q-sphere representation of our output. Let us inspect it. So I'm starting. Initially, we are in state 0. So you could see the one which I had in my slide, vertical arrow mark onto your top. So 0 denotes this particular state. This is your 0. I'm moving on. I have applied a NOT gate. So now I've come down. So this is my 1. I can view via Q-sphere. If I want, I can also go for table view. So table view again, it is inspected from the beginning. So we started in gate 0, your computational basis state, we are in Z basis. So this becomes 0, and probability of measuring 0 is going to be 100%, and there is no phase angle here. Similarly, if I'm talking about 1, we don't have any 1 here right now. Next, I'm moving on. So this becomes probability of state 1 is 100% probability, and 0% probability of measuring 0. Hope you understood. Okay. So is it okay?
And also, can you please take one more qubit and show
Yes, sure.
the table? Yeah.
Okay, let me stop my inspect. Let me add one more qubit. So you want, let us go with 0, 0, 0, 1 and 1, 0 itself. But for us clear for you, let me put. So we are here. Which output representation you want, sir? Q-sphere?
Yeah, table view, ma'am.
Table.
That gives me more clarity. Yeah.
So read your Q0 to your right end. Okay. So if you want, let us inspect this particular circuit. We are initially in state 0, 0. We are initially in state 0, 0. So 100% probability of state 0, 0. I'm adding NOT gate onto my Q0. So what happens? Q0 is flipped. Q0 is your right end. Your right end is Q0. Keep that in mind. Textbooks uses Q0 to your left. We normally use Q0, Q1, Q2, Q3 in any quantum textbooks. But Qiskit alone uses little endian notation in its composer. We have Q0 to your right end, then comes your Q1, then comes your Q2. So this is Q0 and this is Q1. So 100% probability of measuring 0, 1. And let's further know more we have. If you want, I can add a barrier here. Barrier is just for user understanding. So let us add another NOT gate. Let us inspect the circuit again. So we are starting from state 0, 0. So 100% probability of 0, 0. Adding a NOT gate, we are right now in 0, 1. Clear? We are right now in 0, 1. And now I'm going to move on. Shall I click? We'll be into what state? We'll be into state 1, 1. So 100% probability of being in state 1, 1. And barrier is for understanding the code. So in my presentation, you would have seen general circuit for quantum circuit. So this is barrier. This is your input. This is your algorithm. This is your output. Just user readability of your quantum circuit, making it in a readable format. So I could say this portion is my input, this portion is my algorithm or my code, and this portion is my output. Was it clear, sir?
Yes, ma'am.
So I'll be showing you the other bases also. So how to move on from one basis to another basis, and we'll see the table view of this for the other states which we have. So we saw what we have seen till now was how to work on with composer, how to add qubits, delete qubits, add classical bits, delete classical bits. Work on with two quantum gates, which I showed you. One was your NOT gate, another one was your H gate. I'll be talking about H gate in my next slides. So the next important portion of my talk is single qubit quantum gates. So where we have various single qubit quantum gates which are available for us. We have X gate, Y gate, Z gate. We have S and SDG. We rate it as S dagger, and then comes your Hadamard gate. So the gates which we saw right now one was X gate we saw, which was a NOT gate, and then the Hadamard gate also I showed you in my slides, in my demo. So single qubit gates, this was after working out, we have come into this output generation of our various inputs, what will be your outputs. So here, I want all of you to note down or take a pic of this particular slide. It will be helpful when you're working on your own. So the first one is plus, the minus, which we have seen already. Your plus is 1 by root 2 get 0 plus get 1. Your minus is 1 by root 2 get 0 minus get 1. Your I is 1 by root 2 get 0 minus I1. And your minus I is 1 by root 2 get 0 minus I get 1. As we saw, we had three different bases. One was your Z basis, your X basis, and your Y basis. And your various inputs on those bases are, so 0 and 1 for my Z basis inputs. My plus and minus are for my X basis, and for I and minus I are my Y basis eigenvectors, eigenstates. So what we are actually doing is, we are taking for all of my 6 inputs. So I'll take 0, 1, plus, minus, I and minus I, apply NOT gate onto my those states. Okay, so what will happen when I'm applying X on 0? What will happen when I'm applying X on 1? What will happen when I'm applying X on plus? What will be my output when I'm applying X on minus? These are your various outputs. And if you have time and if you're interested in learning into quantum computing, I would suggest start working with the various quantum gates which are available and play on with these all 6 inputs for all the quantum gates which are there. So X gate on 0, it flips. It takes me to state 1. X on 1 takes you to state 0. X on plus does not do anything. It remains, it keeps me in state plus. X on minus, it takes you to minus of minus. And I and minus I, I'm not going into my Y basis for the moment. This is, I want you to take down the vector representation for matrix representation for X. So 0, 1, 1, 0. Similarly, for your Hadamard gate, your matrix representation for your H gate is 1 by root 2, all your ones, 1, 1, 1 minus 1. What will happen when I'm applying Hadamard onto 0? Right now, I showed you this. This takes me to, if I'm on a single qubit machine, if I started from 0, it will take me to 0 plus 1 divided by root 2. So what is this place? Your place is 0 plus 1 divided by root 2. I'm in 50% of state 0 and 50% in state 1. So that is what we have here. So all of your X gate, H gate, Y gate, you can play on. Your Z gate, your matrix representation of your Z gate is this. Z gate, X gate inverted me, right? Z, X on 0 inverts me to 1. X on 1 takes me to 0. Now, Z gate, what Z gate does is, Z on 0 does not do any change. I'll not have any change. I want you to note down this. There'll be no change when I'm applying Z gate onto my qubits, onto my state 0. I'll be only in state 0. But if I'm having 1, it will take me, my phase will be changed. I'll have minus 1 over there. And if I want I, what I can do is, I can come to plus. So I'll start from 0. I will apply Hadamard gate. It will take me to plus. And then apply S gate, it takes me to minus, and it takes me to I, and I can apply Z on I, S on I, Y on I, whatever I want, I can work on. So this is how you create, play with your various quantum states. So if you are done with these 2 slides, we'll just talk about some of the basics here. Your X, Y, Z are called as polygates, and X, Y, Z and Hadamard are also called as Hermitian operators because they have their own inverse. What do I mean by their own inverses? X, if I apply X, it will take me back to my original state. But S is non-Hermitian operator. We also have T and TDG. T and S are non-Hermitian operators, and they don't have their own inverses. So that is why we have SDG gate, S dagger gate. I'll show you in the dashboard of this composer over there. And I will be playing with this these slides. If you're having any doubts, I can show you in the demo part of my single qubit quantum gates using composer. Shall I move on with and show you? Let me stop inspecting this particular circuit. Let me delete this and the one barriers also. So we are just working on with single qubits. So let us delete all qubits. I just want single qubit gates. So Hadamard we saw, let us go for Z. What does Z on 0 do? Z on 0 keeps you in 0 itself. Do you remember that? Z on 0 was 0. I want Z on 1. So how will I do? How will I bring 1? Put a NOT gate before Z. So I'm start. Let us inspect your table view itself. So we are starting. We are in state 0. So computational basis state 0 takes me 100% probability here. I'm moving on to plus. So plus puts me NOT gate. So I'm in state 1. So 100% probability of being in state 1. And now I have a phase angle here. So it is -1, your phase angle. Look at your Q-sphere output realization of the graph. Or graph view of your Q-sphere representation is this color change. Okay, this is for -1. Again, inspect it from the beginning. So let us start 0. So we are at the I'm in 0, so I'm in the top line, blue color. Blue color indicates there is no phase angle here, so positive. Next is not, so I'm moving on to state 1. Now I'm applying Z on state 1. So Z on state 1 takes me to -1. Z on state 1 takes me to -1, and this is my output representation using your Q-sphere. You want state vector. You can also visualize your state vector representation and you can read it here. So here again, from the beginning, let us start. So 0, the state vector representation. We are in state vector here for 0. And then applying NOT gate. So 0 becomes 1. Now I've applied Z on 1. So it has changed a phase angle of -1 plus 0. Understood how this is working? So this is Z on 1 takes you to -1. This particular out. Z on 1, the second one. Z on 1 takes you to -1. Similarly, you can play with all of these transitions. Anything if you want, let us work on. You want me to show anything? So I'll delete that gate here. Let me apply, what do you want? Yes, on IV, right? So H gate, it is applying this gate. So this is your I. So we started from 0. I've applied had a mat, so it has become plus. Now I'm applying S on plus. So inspect this particular circuit. So moving from 0, applying Hadamard transformation, you look into all your state vector, this one, your graph view, your table view, everything you can view on, and your S. This is your state I. This is your state I. So you could see the 1 by root 2 plus I by root 2. So I goes for your imaginary portion here. The real part is 0, the imaginary portion, and look at the color change. We have a phase angle of 5 by 2. More research is needed on these output representations. If at all, if you are taking up this certification exam, majority of questions comes from this particular slide. How the output representations will look like, what will be the output of those. Any doubts? You can play with all single qubit quantum gates. T, this is your T dagger, okay? The dagger symbol, TDG, or this is your SDG. And your poly gates are there, RX, RY, and RZ are rotation gates, square root of X gates. All these gates are very, very useful. Have time to learn about how these quantum gates work, their matrix representations, and what will happen when I apply those gates onto 0, 1, plus, minus, I, and minus I. What will be my output visualizations for all of those input states. Okay. So I'll move on.
Ma'am, we take a 5 minutes break.
Yes, ma'am.
I will post one question to the participants, ma'am.
Yes, ma'am. Yes, ma'am. Yes.
Okay, okay, thank you.
Should I stop
Also,
stop sharing my screen, ma'am?
Yes, ma'am. Also,
Okay, ma'am.
can you share the answers for the questions in message?
Oh, what, sir? I didn't get you. Sir, actually, you want the answers for the poster which you're posting? Let me just stop my screen once. Go to So let me know if you want the answer. So do you want me to give the answer now?
Yes, ma'am.
And the correct answer is 4/5. How do we get that 4/5 is 1/√5. Just share my screen. This is 1/√5 the whole square plus √3/√5 the whole square. Because the question is for, you have to observe this particular state and find the probability of measuring state 0. So sum of your square of amplitude of state 0. So 1/√5 the whole square plus √3/√5 the whole square is going to be your answer. I think I have some questions in chat. Ma'am, it would be helpful. Ma'am, operations, actually, what sort of operations you would like to have? Your plus, minus, your not gates. Gates, you just practice. The other symbols I'll be talking in the next part of my talk. Your multi-qubit quantum gates that I'll be handling. And do you suggest any book websites? Yes, ma'am, I have references, quite a lot amount of references. I'll share it at the end of my talk. And the color representation symbols, ma'am, it comes by practice. You keep watching your various inputs and outputs, find out, right, and keep what it comes, and get familiarized with those things. That it will come by practice. Just remember, blue color is for positive. If you have a phase change, you'll have another one. Again, if I have imaginary, I'll have some purple color sort of thing. So it changes. Ma'am, you want me to wait some wait, ma'am? Sorry, I didn't find that.
Ma'am, shall we start the session, ma'am?
Yes, ma'am. So next part of my talk is multi-qubit states. So I'll be talking about the other symbols which are there in the dashboard of Composer. So multi-qubit states, I hope you're familiar with this. So sum of your squares of your amplitudes should sum up to 1 for measuring them when that is a probability of measuring. And these are, for a valid quantum state, we'll have sum of squares of amplitudes should sum up to 1. So here the gates which I'll be talking about, the first one is C0 gate or Feynman gate, or we call this as controlled NOT gate, and one of the most important multi-qubit gate in Qiskit or in any quantum computing learning. So how this gate works? So here we have the top line, the circled line. This we call it as the control qubit, and the bottom. On the bottom line, we read it as target qubit. So what happens is, if my control qubit is 0, your target qubit will remain unflipped. That is, nothing will happen to your target qubit if my control qubit was 0. But if my control qubit was 1, my target will get flipped. Okay, so the flipped in the sense, if it was 0, it will change to 1. If it was 1, it will change to 0. So this is how it will work. And look at the truth table here. I've taken using Qiskit notation itself. the control qubit, which is Q0, I've taken it to my right, and my target qubit is second one, that is to my left. Okay, so T comma C indicates this qubit is your Q0 and this qubit is your Q1. So when my input is, if the top line was 0, the bottom line was 0, my output is going to be 0, 0. If the top line was 1 and my bottom line was 0, my output will be 1, 1. I hope you are able to understand. If the top line was 1, bottom line is 0, what I said was, if the control qubit is 1, your bottom qubit will be flipped. So 1, 0 will change to 1, 1. Next is, if the top line was 0 and the bottom line was 1, will not have any change. So 0, 1 will be your output. When my top line is 1, my bottom line is 1, my output will be 1, 0. Hope you understood, right? So if the control qubit is 0, the target qubit will remain unaltered. If the control qubit is 1, the target qubit will get flipped. And this is the truth table for, the matrix representation for CNOT gate. Okay. And this is 2-qubit quantum gate. Q0 is your control qubit and Q1 is your target qubit. And CNOT gate plays a very major role in entanglement. Quantum entanglement is one of the major fundamentals for all quantum algorithms, I would say. And this CNOT gate plays a major role for creating entangled states. And the code for doing that, if you're doing it locally, you could create a quantum circuit of 2 qubits. So quantum circuit of 2. If I want classical bits, I'll be adding it as 2, 2. And QC is your, this particular quantum circuit's name. So QC, any name you can give. QC.CX is your CNOT gate, controlled X gate. So CX gate, and I'm applying it on 0, 1. I can also apply QC.CX of 1, 0. That is also possible. And if I use QC.draw, it will draw me this particular circuit. I'll just walk through my slides and then I'll go and show the demo of these gates. Next one is CZ gate, similar to CX gate, but we'll apply Z gate if my control qubit is 1. If the top line is 1, the Z gate notation is this. If the top line is 0, nothing will happen to your bottom line. But if the top line is 1, we'll apply Z gate onto bottom line. So if this was 1, if the bottom line was 0, Z on 0, what it will do? Z on 0 will not do any, will not change. So Z on 0 is 0, so I'll not have any change. So look at this. When my input is 1, 0, that is what top line is 1, bottom line is 0, we are applying Z on bottom line. So Z on 0 keeps 0 itself. But the next one, if my top line is 1, the bottom line is 1, we are applying Z on 1. So here your top line remains 1 itself, but the bottom line changes to Z on 1 takes you to -1. So my output is -1, 1. So here we are applying Z gate exactly similar to your CX gate. Instead of X, we'll be using Z. Z on 0 does not do any change. Z on 1 takes you to -1. Next is swap gate. I can swap 2 qubits. So the values of my qubits will be swapped by applying this. This was again, this is a notation, and this is the matrix representation of swap gate. Next is C swap gate, or we also call it as Fredkin gate, control swap. So if the control qubit, the top qubit is 1, you swap your second and third qubits. If Q0 was 1, Q1 and Q2 will be swapped. If this was 0, nothing will change. These two will not be swapped. Next is Toffoli, and this was the gate which I used for, if you remember in my slides, we used for logical, reversible, and gate implementation. So here, this is a 3-qubit quantum gate. There are 2 control qubits and 1 target qubit. If both the control qubits are 1, my target qubit will be flipped. If both my control qubits, so if my input was 1, 1, and if you remember my reversible circuit for AND gate, I had my third qubit as 0 for my input. So that is, if 1, 1, 0 is passed as an input, my output will be 1, 1, 1. But for all other combinations, 0, 0, 0, 1, 1, 0, 1, for all other combinations, when both were 0, where 0, 1 or 1, 0, my output is going to be unchanged. So here, if you could look at the truth table, for 1, 1, 0, my output will be 1, 1, 1. When both my control qubits are 1, my target qubit will get flipped. When both my control qubits are 1, my target qubit will be flipped. So for 1, when my input is 1, 1, 0, my output is going to be 1, 1, 1. When my input is 1, 1, 1, my output is going to be 1, 1, 0. So the truth table indicates this. Clear? So this is your CNOT gate. I'll show you the demo of CNOT gate and come back to the recap. So the demo of yes, sir.
Sorry for interrupting, ma'am. Madam, I have another question, ma'am. You posted one question, right? You asked us to find out, one second, ma'am.
The probability of measuring 0 was my question.
Correct.
Yeah.
Probability of measuring the 0, right?
Yes, sir.
But in general, there is we can write either in a matrix 0, 1 or 1, 0, right? So in your question, then how do I know which one is a 0 and which one is?
Which one is
equal to 0 and which one is equal to 1?
Sir,
And-
that was, yeah, the vector representation of 1 which I showed you in your, in my slides was, if I had 1, 0, I said it is get 0. Okay. So the top line indicates for 0 state and the bottom line indicates for 1 state. So in the state which I gave you, it was an arbitrary quantum state.
Got it.
It is so the top line is your 0 and the bottom line is your 1. So when they ask you the question for measuring, find the probability of measuring get 0 in the sense you will go for measuring squaring the amplitude of 0, the top one.
Oh, got it.
If it is for 1, you'll go for the bottom.
Bottom. Got it.
Yeah. So let us go for 2 qubit system or 2 qubit. Which gate you want? Any specific? So I have your CX gate. Let us start with CX. I don't want this. Okay, let us start with 0 again. And let me push this. Okay, so let us inspect this particular quantum state at CX gate. Okay. I'm starting from state 0, 0. I've taken state vector representation. So this is 1 plus 0j, 0j. This is for 0, 0. This is for 0, 1. This is for 1, 0. And the last one is for 1, 1. So I'm starting from 0, 0. Applying NOT gate onto my qubit 1. So this qubit 1 changes to 1. So 1, 0. So 1 plus 0j for 0, 1 position. Okay. And now I'm applying CX2. So what does CX do? If my control qubit was 1, my target qubit will be flipped. So my target qubit, initially we had, this was 1, my target qubit was 0. So my output is going to be 1, 0 is your input, your output is going to be 1. Clear? If the control qubit is 1, your target qubit will be flipped. Any doubts in this? So this is how you get your state vector representation. If you want Q-sphere representation, again, let us inspect it for another one for Q-sphere to show you. Let me inspect this for Q-sphere just to show you various outputs which I have. So I'm in, and there is another representation of states in Qiskit. One is Q-sphere, the other one is block sphere. Okay. The interview question which I had when I appeared for Qiskit Advocate was, what are the two representations which you have, and what are the differences between them, and by which one you will choose? Okay. The representations are, one is Q-sphere, the other one is block sphere. I can visualize Q-sphere using my composer. Block sphere, I can't visualize using my composer. I have to install Qiskit locally and visualize block sphere in my local machine. So this is one difference. Basically, the difference between Q-sphere and block sphere is, Q-sphere is actually this goes for two-dimensional view, whereas block sphere is multi-dimensional view. First difference, Q-sphere is two-dimensional and block sphere is multi-dimensional. Second difference is, I can show phase change, that is the color changes using Q-sphere, whereas block sphere will not show us phase change. It will only be blue color wherever I look at. This is your second difference. Third difference, Q-sphere uses a single Q-sphere for all your qubits. If I'm having 3 qubits, I'll be using one Q-sphere only. If I'm having 4, if I'm having 5, in a single Q-sphere, I'll be representing all my qubits. Whereas when I'm talking about block sphere will use separate block spheres for each qubit. So if I'm talking about a 3 qubit system, I'll have one block sphere for Q0, another block sphere for Q1, another block sphere for Q2. So these are the major differences. So you choose whichever you want. If you want 2D view, you can go for Q sphere. 3-dimensional, you can go for block sphere. If I'm interested in color changes, phase change, and all those things, I can go for Q sphere again. Okay. So depending upon the algorithm or depending upon the need of the programmer, he can choose whichever design he wants. Okay. So now let us inspect this particular output. So we are starting from 0, 0 here. So this becomes 0, 0. And I've applied NOT gate onto my bottom qubit. So bottom qubit visualization. The top qubit is 0. So Q0 is your right hand and Q1 is your 1 now. And now I'm applying C0 gate. So now what will happen? Your top line is 0. Your top line is 0, your bottom line is 1, so there is no change after applying CX. Clear? Only if my top line is 1, I'll have a change. So for that, if you want, you can add a NOT gate here. Inspect the circuit again. So 0, 0. Shall I take table view? So that it is readable. 0, 0. Let us start initially. So 0, 0 probability is 100%. The next one, I've taken 1, 1 to both of them. So 100% probability of basis state 1, 1. Next is I've applied CX. So 1, 1 will now change to 1, 0. 1, 0. So 100% probability of state 1s. Clear? Any doubts, anybody? This is how your CX will work. Let me add another qubit. You want control swap to be shown. Where is my swap? So let me delete this. CZ you can play like this itself. So control swap. How to add a control is click on the swap and add control over here. Q0 I'm adding control. Okay. So this is Q0. So add Q0. So this change comes out. Understood? So let us inspect this. I'm starting from 0, 0. Being a 3 qubit system, so you'll have 0, 0, all your combinations. 0, 0 to 1, 1, 1. Okay, all 2 to power 3 combinations we have. So initially we started from 100% in state 000. I'm moving on. But the first 2 qubits are 1, 1. So the first qubit, Q0 and Q1 are 1 and the third qubit is in 0. So 100% probability of being in the state. Actually, if you want, you can read it from right hand, 1, 1, 0. And now I'm applying control swap gate. So if the top qubit is 1, the control qubit is 1, the bottom, these 2 qubits will be swapped. So this was 1, this was 1, 0. So my output is now going to be 1, 0, 1, 1, 0, 1. Clear? You can visualize using Q-sphere, you can visualize using graph view, table view, state vector representations, whatever you want, you can play on. Any doubts, any gate you want, if you want, I can show you. Just play with these. Ma'am, I hope the other symbols are covered. I have not touched rotation gates. It will take time for me to know. I've just spoke about all single qubit quantum gates. And 2 qubit gate swap, control swap, CCX, similarly like CX it will work. I gate is your identity gate. Applying I onto a state. It will not do anything. You can play with quantum gates. I would keep my majority of my questions for my students from quantum gates. Those 2 slides, I could even go for even 50 marks. I can take questions from those. Play with all quantum states. For various inputs, whatever outputs you're getting, what is your state vector representation? Your Q-sphere draws them to draw Q-sphere, asks them to draw block sphere, any ways. And what will happen when I'm applying H and H continuously? Similarly, any combinations of gates, what will be the output. So till now, what we have seen was difference between bits and qubits, how to differentiation between reversible circuits and reversible circuits, how to create quantum circuits using IBM Qiskit. Basically, we saw about various single qubit gates, multi-qubit quantum gates, which are available. And the visualizations which I showed you in the demo was one is probability, that is histogram representation, state vector representation, and Q-sphere representation. If you're having any questions, I could like to take your questions. Otherwise, I'll move on with quantum entanglement. Shall I proceed with quantum entanglement, or is there any questions?
I have one question, ma'am.
Yes. Yes.
So
Yes.
work on this quantum computation. So every time we need to set all these qubits and everything.
Yes, sir. Yes, sir. It is similar to what your inputs are. You're writing a program, you're getting inputs from the user. You write an algorithm to work on those inputs to get what output you want. That's the same. So work with design what gates you want. That using gates becomes your algorithms, the actual algorithm.
Okay.
Yeah, there's a question in chat. Ma'am, can we perform QA/OA optimization technique using this quantum circuits composer part? Ma'am, if it is for 4 qubits, it can work. If you're having more a number of qubits, composer will not support you. You have to install Qiskit locally and then use. Chitra ma'am, how do you get that X symbol? Ma'am, X symbol is not gated. The slides I've used.
Ma'am, I have one question.
Yes.
The initial condition itself is 0 actually for
Yes. For all qubits start
why
with
we put again all qubits start with 0, then why we put again 0 in the problem?
Sir, just to show you what 0 looks like.
Oh.
It's not needed.
Okay, thank you.
It's not needed because when I was inspecting, directly it take me to my output slides, right? So I thought let me start from 0 and then walk. This is just for your understanding. How many qubits composer will work, ma'am? It will work for 4 qubits, ma'am. Composer will support 4. Not more than 4. Okay, ma'am. So moving on.
Ma'am, question, ma'am.
Yes,
Suppose I want to work on more bits, then is there any other source is available, ma'am?
Yes, ma'am. You can install Qiskit locally. You want me to show? I've installed upon Anaconda. You can go for. You should install it, ma'am. Upon Anaconda, you can install Qiskit and you can work using your Jupyter knowledge. So I could take any example which you want. Multi-qubit quantum gates. So you install locally and you work on. So this is the code. Imports whatever you install, pip install Qiskit upon Anaconda and you work on. This is one way. Another way is you can also go for Colab. Colab, no installation is required. You can just go open a notebook, work using Colab. QBraid also, QBraid. Create an account in VRAID, QBraid. This also helps you to work using local notebooks. So you can increase your number of qubits here. So this is the demo for C0 gate, what happens, measuring it. This is Blocksphere output, the one which I didn't show in Composer. So this is Blocksphere. It uses different Blockspheres for each qubits. CX gate and so on. So this slide will contain every output, your histogram, your Q-sphere, your circuit diagram, all of for all your gates, your state vector representation, anything. If you want, I can slow down. For more a number of okay, ma'am. For more a number of qubits, we go for local installation of Qiskit and work on it. So this is CCX gate. So 1, 1, 1, my output will be 1, 1, 0. So if you could see, read up this, your output will be executing it on getting the state vector representation. So 1, 1, 1 was my input, control group, so 1 was. Again, when I'm measuring, what is going to be my output? So 1, 1, 0. So Q0 was 1, Q1 was 1, Q2 was flux speed representation. Your Q speed representation of 1, 1, 0. This is 1, 1, 0. Q0, Q1, and Q2. Your histogram representation of 1, 1, 0. So just play with all of these things when you have time. I would suggest if you are beginners, rather than locally installing Qiskit and working on, start working using Composer and then work with the nodes.
Madam, I have another question.
Yes, sir.
So I'm in impression when I work on a composer, then I mean it interact with the qubit or it works on qubit. But when I install it in a local, technically it is working on a transistor, right, ma'am?
Yes, sir. Yes, sir. So here again, it depends on where I'm executing my code. So I have a run execute operation here. I'll be choosing a backend. Here I can choose devices or simulators. Earlier we had simulators. Nowadays we don't have simulator. So for Qiskit V2, we work only on real quantum devices, where I will use my quantum. I'll be using my ID there. Okay. You'll be using your token ID for working on to Qiskit. So the version which I'm using, so if I'm using in the latest version Q2 V2, version 2 of Qiskit, I have an instance created, and then I can use my API ID and CRNA. This is what it helps me to run it on real quantum device. So I can execute on the device which I want, and I can give those devices the Qiskit runtime service, what are the devices which are available, and how I can execute my code. So you could choose your things, installations. Again, it will take time for early beginners to work on. Is that clear, sir?
Yes, ma'am. Thank you.
Ma'am, I have another 15 minutes. Shall I skip entanglement? I'll go to how to become a Qiskit advocate and so on, or just run off with this entanglement. Take 5 minutes in entanglement. What do you want me to do?
Yes, ma'am. Yes, ma'am. Please proceed.
Yeah. So entanglement is you can behave exactly the same way sitting in a remote place. So if I'm sitting here and my friend is in US, if I'm ordering coffee, cold coffee, my friend will be automatically delivered a tea, or he'll be automatically delivered a cold coffee based upon my code for creating an entanglement. That is, they will exactly behave the same way or exactly behave in the reverse way. So we'll all have friends who'll always say yes when I say yes. I'll also have a friend who'll always say no when I say yes. Okay, so those things can be created using quantum entanglement. So I'm skipping off and talk about these things a little bit later. So how to create entanglement between two qubits is the circuit for creating entanglement is the Hadamard gate and the CX gate which we saw. So I'll show you this in the demo portion, and I'll share the slides with ma'am so that you can share it with your ones. So just keep in mind, this is the circuit for creating entanglement. I'll show you this in the demo and the composer here. So entanglement, I just want 2 qubits. I'm deleting this. So I don't want this. I'm just starting off with 0, 1, putting a Hadamard gate and then a CX gate. Okay, so how do we create entanglement between two qubits? So the circuit for creating entanglement between two qubits is if the control qubit of your CX is in a superposition state. I repeat, I can create entanglement between two qubits if the control qubit in a CX gate is in a superposition state. So what do I mean by superposition state? I'm in 50% 0 and 50% 1. Let us inspect this circuit to make you understand more clearer. I'm starting from 0, 0. This is optional. By default, all quantum states are in state 0. Just have taken 0 to show you that, yes, we are starting from 0, 0, just for that case. So I'm in 0, 0, 100% probability of 0, 0. I'm applying Hadamard gate. So Hadamard takes me to, puts my Q0 into 50% 0 and 50% 1. So look at this. Your Q0 is 0, which is 50%, and your Q0 is 1 here, which is again 50%. Now I'm applying Hadamard CX gate onto this. So what will happen? When this was 50% 0, what will be my output? Any answers, please? Can any one of you unmute and say me what will happen? When this was 50% 0, my bottom qubit is 0. Will it change? No, right? So when this was 50% 0, my bottom qubit is going to be 0 itself. But when 50% 1, my bottom qubit is going to be 1. So my output after applying CX onto the control qubit was in a superposition state is going to be 0, 0 plus 1, 1 divided by root 2. 0, 0. 0, now I'm applying CX. So now after applying CX, I'm in state 0, 0, I'm in state 1, 1 for 50% of my time. So 50% of my time I'm in state 0, 0, and 50% of time I'm in state 1, 1. This is how we create entanglement. And entanglement here, the friends are, that is, if the bottom cube, if the Q0 is 0, automatically my friend on the other side will also be 0. If I was 1 in state 1, my friend on the other part of the universe will be in state 1. So how entanglement is playing a major role in quantum key distribution and all applications of quantum algorithms is sitting here, I can find out what is happening on the other part of the universe. So if I'm in state 0 and if me and my friend are entangled, I could say he'll also be in state 0. If at all, if my circuit is this. Quantum teleportation is another important application of entanglement, where you can teleport the value of one qubit to another qubit on the other part of the world. So you can send between Alice and Bob and see what is actually happening, and where entanglement plays a major role. So here, this is a fundamental circuit for creating an entanglement. Friends behaving in exactly the same way. If I want friends to behave in an opposite way, I can create circuits. This is the truth table here. If my input is 0, 0, I can create friends behaving exactly the same way. If I'm input is 0, 1, how will I take my input to be 0 and 1? The top qubit is 0, the bottom qubit is 1. I'll get my friends behaving exactly the opposite way. So if I'm 0, my friend will be in 1. If I'm 1, my friend will be in state 0. If I want a phase change, this is the same 0, 0, 1, 1, but with a phase change, my input should be 1, 0. If my input is 1, 1, I'll have the second one in with a phase change operations. Friends behaving in a different manner with a phase change. So this is the fundamental circuit for creating your entanglement. And you can play with this truth table. Apply X gate here, apply X gate here, and you can generate all of these that I'll show you here. So circuit diagram, histogram representation, state vector representation, and Q-sphere representation. So this is a fundamental circuit for creating entanglement. So H and CX. So this is your state vector representation, this is your Q-sphere representation, and this is your histogram representation. Similarly, if I want to create Bell state 2, what is that? Entanglement is also called as Bell states. We also call them as EPR states, named after the scientists Einstein, Podolsky, and Roshan. So this is the circuit for creating Bell state 2. The Bell state 2, which I mean, is from the truth table. This is Bell state 2, Bell state 3, and Bell state 1. So you can create all of these 4 entangled states just applying X gate onto your entanglement. So X on top qubit, X on bottom qubit, X on both the qubits. X on both the qubits will give you another output. So these are the various visualizations which you can work on. Output visualizations you can work on with when you're having time, you can work on. I'm just skipping off GHZ, all these. I'll just talk about one of my question will be width and depth. So what do I mean by depth of any quantum circuit is how many qubits in which I can parallelly work. So if I'm talking about the depth of this particular quantum circuit, this can be done only after this. So this portion can be done only after this. So this is 1, 2, 3, and for measuring also we have 1. So depth becomes 4, and width is the number of qubits. So how many qubits? We have 3 qubits here. So the width becomes 3, and the gate counts, GC is your gate count. How many gates are there in this particular quantum circuit? So this is how you calculate the depth and the width and the gate count for a particular quantum circuit. So things which I've covered here, objects which are entangled share a defined relationship. So if I'm entangled with another qubit, we'll behave exactly the same way or exactly the opposite way. Measurement of one qubit affects the other qubits. Entangled states cannot be factorized. You cannot factorize 2 entangled states and write them separately. Okay, so that is difficult. Entanglement are called as Bell states or called as EPR pairs. The code for Bell states, the circuit I've shown you, visualizations, histogram, state vector, and Q sphere. I didn't speak about GHZ circuit. Depth and width we saw. We didn't talk about classical logic. So I just take 5 more minutes for how to become an IBM Qiskit advocate. Make contributions to Qiskit code and community. Attending a quantum computing session also counts towards contributions. And read this particular blog for eligibility criteria. If you want, I can just copy these links into the chat for you to You're posting second questions. Should I wait, ma'am? So meantime, shall I copy these things?
Okay, ma'am.
Yes, ma'am. Yes, ma'am. Second question also same, ma'am. So I didn't check the questions. Can you read out the questions?
No. So in second question, you are asking to find out the key one. I mean, probability
For 1, no? Okay. Ma'am, should I wait or proceed? For implementation, you can use more number of
Ma'am, I have a doubt. Many courses that Qiskit Advocate program and certification programs, those things you have posted, right, ma'am?
Yes, ma'am. I'll talk about that once.
Which one is the beginner? Which one is the beginner?
That's what, ma'am. In the beginning, in the early part of my talk, I spoke about you have tutorials, composer, you'll have certifications. That's what once. There is a learning portion in IBM Quantum Cloud.things. The first one which I want you people to look into is look into Quantum Business Foundations batch. This one in your learning platform, IBM learning platform. First one is this. Second one, you can move on to basics of quantum information, fundamentals of quantum algorithms. Third one, and then you can expand whatever you want. If you are good at PML, if you are in quantum chemistry, variational algorithm design, you can move on. If you are in need of fundamentals like quantum mechanics portions for computer science people, these are quantum algorithms. I was talking about uses Joza algorithm, quantum key distribution. Modules are really good learning to keep your learning for computer science perspectives. And there are YouTube videos on Qiskit, tutorials available. And Composer is what I showed you, right?
Madam, which course is related to qubit gates?
Quantum gates, this algorithms, this one second. I'll just copy that blog 1 second. Yes, my chat. Ma'am, Composer only 4 qubits. For local installation, you can work for more number of qubits depending upon your system which you are going to work with. The device which supports. So for the device, if I'm running it on real quantum device, Heron will go for 127 qubits. Torino also. Depending upon the device which you're using, you can increase your number of qubits. But for Composer alone, it will go for 4 qubits. Here I have eligibility criteria. There is a block here. Just click on that link. And this is applications are open throughout the year for Qiskit Advocate. So you can open, you can check into this. Here version V2. Here they would have given you basics of quantum information badge or fundamentals of quantum algorithms badge, the one which I showed you right now. So any of these two, if you complete, you can apply for Qiskit Advocate to become a Tier 0 advocate. Or normally, we used to have global summer schools which are happening once a year. If you have participated and if you have received an advanced badge for Qiskit Global Summer School 2025, you could apply directly for Qiskit Advocate. This is over actually, so right now it's not available. But for our new people, you can either complete quantum information badge, fundamentals of quantum algorithms badge. We'll also talk about single qubit machines. Just click on those things, sir. They'll give you a lot of. So you have algorithmic. This is fundamentals of quantum algorithms, phase estimation, Grover's. I think Triple IT there, the professor at Ashwath will talk about quantum algorithms. And if you are interested for quantum information batch, this will talk about the things which I spoke today: single systems, multi-systems, quantum circuits, entanglement, and action. You can take up this exam. If you have understood my session, I could say give a kickstart to this particular basics of quantum information material and take up this badge. You'll be given a creditly badge like this, and you can apply for Qiskit Advocate. Is it out clear, sir?
So you said you want to post some blog on qubit gates.
Not a blog necessarily, sir. They look into contributions, like what sort of contributions you have made to Qiskit community or anything. Not just contributions to Qiskit alone, or quantum computing also. Anything you would have done, but learning now. Earlier we had these things, but now they have said either of these batch if you have, you can apply, and maybe they might have some. I'm not anywhere related to IBM. I'm not an employee of IBM. I'm an IBM Qiskit Advocate only. They might have some filtrations upon checking out to be given or not. They decide. They make the decisions. So this is for the application form. If you have completed that badge, you can take those two of any of those two badges. You can submit your application here. All these links I've copied in chat. And this is for developer certification V2. I took up V1 only, V0 only. I have not yet taken V2 certification yet to complete, yet to take this. And for learning resources, I would say Slack is a very nice place to communicate. Earlier, I was working all alone in quantum computing, but now I have an entire community. So many people I have. There are so many channels which are available here. So you can speak with your friends. You can connect with all other like-minded people. So when I was working all alone from 2003 to 2015, I could say I have a plenty amount of people here. We have lock channels for Quiskit advocates, for mentors, for IBM Quantum Challenge mentors. We are being given opportunities for becoming mentors in challenges or things happening around the world. We have a meeting next week for Quiskit advocates in Bangalore, and I'm attending it actually coming Thursday. So we do connect, we get connect with various Quiskit advocates over the world. And this meeting is for India Quiskit advocates. And this is a place where we communicate. We use Discord, we use Slack for communications. If you're preparing for certification exams, I would say these channels will help you. Quiskit Cert exam channel, Quiskit 101, all those channels will help you a lot. So I could say general channel, India channel. So for students, quantum internships channel, textbook reading groups, undergrads, Quiskit Cert exam, all of these are really helpful in Slack. And this is the one which I showed you for learning platform. And benefits, Quiskit Advocate Mentorship Program QAMP, where I've worked on nearly 7 projects in QAMP, mentor in global summer schools, mentor in IBM Quantum Challenges, organize Fall Fest events, invite speakers as I'm here today, Advocate Cafe, where I'm paired with another advocate on the other part of the world, IBM internships, hardware and software, collaborations, connected with new people. And these are other things. You can participate in hackathons, not just IBM's, you can also go for Microsoft's, Google's, Xanadu, Rigetti, NVIDIA. They all host hackathons, global summer schools, quantum computing challenges over the world, all over the world throughout the year. Various online courses from IBM, QWorld, Dominium, get certificates from QWorld. There's so many certificates, like I've completed all of these: Q Bronze, Q Silver, Q Zinc, Q Mercury, Q Nickel, and Q Cobalt. For references, some of you asked me, these references will be for the basics. Textbooks, I would say I started with Nelson and Chang in 2003. And for reversible computing for my PhD, I've worked more on to these papers. Alex DeVos, Rich Lesser, and Willie. For Quiskit, James was a person who's working on quantum music. He's learning Carnatic music for working on to quantum music. Frank, these 2 people are for Quiskit certifications, pocket guides, Quiskit release, and also. And these books are really good. Thomas Wong, Robert Sutter, Dancing with Qubits, really nice textbooks to work on. I would also suggest Venkata Subramaniam's National Quantum Mission of IBM. And these are our papers which we have, our papers. These are the projects which I've worked. I've worked on a project with Nati of Classic. And all these people are again quantum experts over the globally. So we worked for a 4-month project where we worked on designing interactive introduction to QC course with Classic. And the others are QAM. So all are Quiskit advocates. The first one was I started with Julian. He's from IBM Switzerland. Learned a lot amount of things, and for all of these projects, I was a mentor here. We actually translated Quiskit textbook into Tamil language in hardly 3 months of time, and I would proudly say it was entirely done by the students and some of our staff members of CIT, where we converted the entire textbook into Tamil. But right now, the older textbook versions are not used, so those versions are not right now available. But we worked on the entire translation of Quiskit textbook into Tamil language. So thank you all. You can reach me at my mail ID or my LinkedIn ID. I wish all of you happy learning quantum computing. Thank you, and wishing you enjoy learning. Yes. Hope my session was useful for you. Being a remote session, just looking into a system and talking is really very difficult from my side and from your side also. Anyways, happy learning quantum computing. Thank you.
Thank you, ma'am.
Thank you, ma'am.
On behalf of all the students and faculty members, I sincerely thank our respected guest, Dr. Manjula Gandhi, for taking the time to share such valuable insights with us. Your session helped us understand exciting topics like Qiskit Composer, working with single and multi-bit qubits, the role of quantum gates, as well as fascinating topics like Bell state quantum entanglement. Learning how to use Anaconda as a platform to explore these ideas was especially helpful. We're truly grateful for your guidance and for opening our minds to the possibilities of quantum computing. Thank you, ma'am, for inspiring us today. Thanks to all the faculty members for taking your time. Thank you so much.
Thank you, ma'am. Thank you.